Well, welcome to Lecture 3, the review of signal systems and digital signal processing. As you can well imagine, there's a lot to this topic, and I've got 79 view graphs here, so it'll be a bit longer than the last one. I'll probably break this lecture up into 4 pieces, and we'll stop at about somewhere in the low 20s of view graphs. And then one at a time we'll move on. Signals and systems and digital signal processing are a part of radar that is not really required until a number of lectures later in the course. So I'm going to be a little leisurely about probably getting these sets of lectures up, but they'll all be up well before, I would guess, within the next 4 or 5 lectures. So let's move onward. Here's this particular view graph. We're going to see every single lecture just about. And it's to put into perspective the subject that we're studying and the lecture that we're working on. Here we see the path of energy coming from the antenna, reflected energy through the transmit-receive switch and into the receive chain, and then on to an AtoD converter. And this, of course, implies that we're transforming the data from the analog received echoes to the digital domain where we do signal processing. And signal processing algorithm technology has improved drastically over the years because we're able, with the progressions in Moore's law of being able to do enormous amounts of digital processing, we're able to do extremely well. Giant strides in radar have been made over the last decades and are continuing to be made because of the advances in processing power and in the power and the attributes of AtoD converters. And here we see what that analog signal strength coming in, the echo. This is probably the noise background, and here's the backscatter from a rain cloud, and here's a target. Probably it's a significant amount above the noise background. Okay, we apply signals and systems and digital signal processing on the received signals, and with the hope of implementing optimum target detection, the best that can be done. Okay. Signals and systems and digital signal processing each are usually 1-term semester advanced undergraduate courses for electrical engineers. And digital signal processing courses at the graduate level go deeper into the subject and into sub-areas of digital signal processing. Many people do their PhDs in signal processing, digital areas of digital signal processing, which has gotten to be an extremely complex subject matter. And so in no way can I give you justice to the huge amount of material one would like to know, or to the material you should really know. What I'm going in this 1+ hour lecture, what I'm going to do is I'm going to go over the highlights of what you need to know. And if you can click through these view graphs and they say, yep, you're in good shape. And it'll let non-EE majors know if they need to study the material in more depth to understand different areas of the course later on that you need this for. Now, the University of California at Berkeley has a superb online signals and systems course that delves into the digital domain too. And it's you can pull down these lectures, download them, and watch them free at webcast.berkeley.edu. And here is the website of the course given in spring of 2007. Probably the godfather of digital signal processing in terms of developing the formalism that was put in books was Al Oppenheim and Ron Schaefer in the text they put together. And their MIT professor, Alan, and Ron Schaefer, I believe, went to Georgia Tech. Now, one of Alan's great graduate students, because I looked up his biography of the teacher at Berkeley, was the fellow who teaches this course. And he got all kinds of teaching awards at MIT when he was a graduate student and a postdoc, if he was that. But I just noticed the slew of awards that he got for teaching. And I'm watching his course, bits and pieces of it. He's a damn good lecturer. So, and when you go to the main web page, the upper right-hand corner, it'll say Spring 2011, and you have to just pull that down and find ECE 120 the last time it was given. But I know in the spring of 2007 they recorded ECE 120 with the professor from Berkeley that I mentioned to you before, and I know that that's a damn good lecture series he gives. Not just in the material, but in his presentation of the material. Now, signal processing in general is the manipulation and analysis and interpretation of signals. It's sort of like a dictionary. What it includes is an awful lot of radar-type stuff and processes, adaptive filtering and thresholding, spectrum analysis, pulse compression, you saw that in one of the boxes, Doppler filtering, you saw that in one of the boxes of the block diagram of a radar, image enhancement, many radars do imaging and you can enhance the image, adaptive antenna beam forming and beam nulling, but also lots of other non-radar stuff, image processing of pictorial images and speech processing. They're all areas signal processing delves into and does a great job at helping you enhance you do those functions. And again, it involves the collection, the storage, and the transformation of data, both in the analog and the digital world, and now mostly we do it in the digital world. You need a lot of horsepower. You need lots of, not just, terabytes or teraflops, megaflops or gigaflops. You go way up there. And as fast as the circuit designers, the chip designers can get more flops out of their processing power into solid state technology, the processors are there to use it. And so a lot of horsepower is required, not just a general purpose computer, as can be done quite readily in other functions. Okay, now for continuous signals, let's take a look at that first. This is just to go over and set the stage and the definition and work our way up so you'll understand the terms. Here are three typical examples of continuous time signals. We've got some sine waves in them, linear function of time, and powers of time. And the output here for a random signal, I just drew this with Adobe Illustrator. It's a continuous function of time. Okay? Now, if we add periodicity, horse of a different color. This is a non-periodic signal in that it's 0 before, the x of t is 0 before 0, then it's non-zero, and then it goes down to 0 after, let's call capital T the length of the signal. A periodic signal has the form x of t plus some delta t, the period say here, is equal to x of t. So that defines the difference between periodic and non-periodic signals. There could be a bunch of zeros here, the same number here, and the same number here, separating the non-zero parts, and it still would be periodic. Now, you can have complex periodic signals, of which the reflection off of a target, its electromagnetic wave, is a good example. But that's a non-periodic signal. It's a complex signal. There'd be a real part and an imaginary part. Okay? And we see this, and here I'm just drawing a real part of a signal and an imaginary part. And at each moment of time, you could define x with a twiddle is equal to the real part here plus j times the imaginary part. Now let's define the concept of a continuous linear time invariant system. And define it this way. If we put a signal in that's continuous and we get an output y of t, then y of t is equal to an operator operating on this x of t. It is said to be continuous, linear, and time invariant if x of t and y and t are continuous functions of time. Then the system is a continuous function of time. The system is linear if you do the transformation on a linear set of these functions, and you get this output for the two y's, for these two x's. And it's time invariant if time shifts in the input give the same time shifts in the output. So there we have a continuous linear time invariant system. Now let's look at the concept of a delta function. The properties of the delta function are that it is 0 for t not equal to 0, and it's infinite at time t equal to 0. And the integral of a delta function over all time is 1. Now when you put that delta function into as the input in a continuous linear time invariant system, you get as the output what we call the impulse response of the system. We put an impulse in. H of t is defined as the impulse response of the system. Okay? Now let's again look at these, let's again look at these two systems where we have x of t in and y of t out, and the delta function in and the h of t out. The definition of a convolution of two functions, I'm just going to define it by this definition and then use it, is if we convolve x1 of t and x2 of t, and that's defined as the integral from 0 to infinity of x1 of tau times x2 of t minus tau. Notice that's reversed and shifted, integrated over tau space, which goes from 0 to infinity. Now for linear time invariant systems, the convolution of x of t and that unit impulse response is just y of t is equal to x of t convolved with the impulse response of the system. And here we can write it. And we're going to see in the digital world there'll be a similar form for it. So why not analog systems? Why don't we use them to calculate in sensors and different systems? Here are some that are a darn good example. Our good old slide rule. Good to 2 places if you're lucky. And if your hand is a little jittery, not even that. So there's the repeatability issue. And they can add, subtract, multiply, divide. Not add, subtract, but multiply, divide, and do square roots and logarithms. And a voltmeter. It's much easier if you have a digital voltmeter that just spits out 2 numbers. You don't have to read with your eye. If the hour was between, is this 1.6 or 1.7 volts? Where full scale would be 10 volts. And here's from World War II, a torpedo data computer, which is to take as input information the state vector of the submarine, the angles of the measurements of the target with the periscope, and spit out as output when the torpedo should be fired, in order that a freighter or a battle or a ship or what have you, there'd be an intersection between the torpedo and the ship. It would generate the firing solution, and with lots of knobs, and this is all full of mechanical wheels and ratchets and things. Very big, probably the height of 4 or 5 feet, cramped in a submarine. You see it's bending here to make room for the hull, as the bent hull in a World War II submarine. Now certainly a microprocessor and the keyboard would take up more room than the crunching to do this, for that one function. And of course a $5 hand calculator would do circles around a slide rule. So let's look for a couple of minutes at sample data and discrete systems. Now, digital signal processing deals with sampled data. Okay, so it differs from processing continuous or analog signals. And the way it differs is we obtain the digital output by a sample and hold amplifier followed by an analog to digital converter. And so what that does is it takes the analog signal, samples it, holds it, and during that small element of time reads out a digital word length in ones and zeros. And then quickly goes back and samples and holds and samples and holds. And one of the characteristics of it we'll get into a minute, but here's a simple visual of sampling. It converts a continuous signal, a continuous sequence, here a sine wave, through an analog to digital converter into a discrete time system, which we denote x with brackets and an integer. And the integer has swallowed up in it usually the time between samples. If we were more interested in this as an exact physical number, and this was time, it would be n delta t, being the delta t, or t being the period between samples. And radar signals are complex, so you're going to sample in the real and the imaginary part of the signal to get out to the radar data. Now let's look at AtoD conversion for a bit. Here we see that process where we take a continuous signal in and come out with a digital time sequence. And this is visually what would come in versus what would come out over the range, the full scale of the AtoD converter. And you see that there's a quantization level, Q, and the probability density function of that error in the measurement of voltage is this. It goes from minus Q over 2 to plus Q over 2, stating just that you don't know where the real signal is within the increment of measurement. And we assume it's uniform. And the standard deviation of that error is just Q over 12. And where the error is the output minus the input, here we just plot that. Here we plot the error. And you can see it goes back and forth between Q, minus Q over 2, and plus Q over 2. Now, there's a lot of imperfections that happen in the real world when you build one of these beasts, especially when you want it to be linear over, say, 60 dB of dynamic range, and you want it to sample every 10 or 100 megahertz, megasamples per second. And these are the kinds of errors that you can have. You can have an error in gain, an offset, missing bits, a lack of monotonicity, nonlinearity, and all these different things can happen. And these are things that when you go to purchase an AtoD converter, you have to understand that you're getting the real deal and set up systems so that a product coming out you know is that good. Because if you have a nonlinear box between your analog signal and where you're doing your digital processing that's optimum, that nonlinearity transformation in the AtoD converters can give you big problems if the nonlinearity is large enough. And we'll go on to the next segment. Here what we've done is we've taken a pure tone at 5 megahertz, or what we think is a pure tone, and we put it through a spectrum analyzer. And we see the peak of that goes way, way, way up. And roughly the floor is at minus 80 dB and a little above 0 dB power level, probably 5 dB above. And dBm is the 5 megahertz tone. Now, we refer to the Spurfree dynamic range as the distance between the peak of the fundamental and the highest spur. That is the highest side lobe that comes up. So this is just a definition of the Spurfree dynamic range, where here is the background. Okay? Now, for an ideal AtoD converter, the signal to noise that we can linearly work over is 6.02 times n plus 1.76 dB. Where n is the number of bits in the AtoD converter. And now on to the AtoD word length, and to let you know how many words you need for a given